after understanding the exact differential equations for their solution and their identification, now we will consider situations where we do not have exact differential equations. Instead, we have inexact differential equations. And what is the treatment that we can do in order to make them exact differential equations, and then we could be able to solve them. So the equation, that condition of the exactness test is this, but in this case it will not hold, that is, it will not be equal on both sides. So the thing that we can learn from this test is that m and n are these values that determine their equality, if they will be equal or not, greater, equal, or less. So it revolves around the values of m and n. So in order to get the equality in this exactness test condition, we can focus on the values of m and n, because these are the values that are substituted in this test, and if we change their values, definitely the result can change, that is, the inequality can turn into an equality. So this is the gist behind our process of finding the treatment. Now the basic thing behind the exact differential equation is the presence of total differential, and total differential suggests that if we differentiate the given function, it should be equal to 0, because on the right hand side we have a constant. So in this case, when we do not have the exact differential equation, rather we have an inexact differential equation, we will not have the equality in this case, so that this term will not be equal to 0. So you can refer back to the definition of exact differential equation, and then you can compare it with the current situation where the equality will not hold. Now, as we remember that m and n can be changed, how it can be changed, let us make some adjustments for that. So what I can do is I can multiply the equation with a certain factor, which I am calling as f(int), that is factor. Int stands for integration, so it is integrating. So it is basically integrating factor that we are talking about, and if we multiply it with the equation, there will be changes. Why we call it integrating factor is something we will find out once we solve this. So this was the left hand side before, and this was the right hand side. Now we have the integrating factor introduced on both sides as a multiple. So there are two effects. One is that the value of m will change. Now as you can see, the value is now different. M is getting multiplied with f(int), that is integrating factor, and n is also not the same. Now it is n into integrating factor, that is f(int). So this is the first change that we can note. The other effect is that the equality will remain there. The other feature should be that the equality is still there, because the integrating factor was multiplied on both sides. So equality will remain equality because something is multiplied on both sides. So it means that we have retained the equality. Equality is still there, and the values of m and n have changed. So this is the right thing to do, that is, without affecting the equality, we are changing the values of m and n. Now we call it integrating factor because it's a factor, it is getting multiplied. As you can see, it's getting multiplied. Secondly, it is integrating factor because in the background of this exact differential equation, we know that there is total differential, and that total differential would be exactly equal to 0, as we have seen before. So when we have inexact differential equation, it will not be equal to 0. But if we introduce this integrating factor, the total differential will become equal to 0. And once if the total differential is equal to 0 of this function, that is, it should be equal to 0, it means that if its differentiation or differential is possible, its integration will also be possible. And if we take the integral of its differential, then it will be equal to, then it will be equal to 0. It will be equal to the original function. So it means that it is enabling us to integrate the function and get the same answer after taking its differential. So it was about why we call it integrating factor. However, the main thing is that we need to find out how we actually introduce this factor. There are two ways. One is the trial and error crude method, and the other is the formula method, which is more scientific. Primarily we start with the trial and error method, and it's very easy because what we will do is we will experiment with different values. As integrating factor, we will assume that integrating factor is equal to y, and if this fails, we'll experiment with t, and then if it fails, then y square, and if it fails, then t square. So in this way, alternatively, we will introduce these variables and we will increase their power just to see that which one of them serves as the integrating factor. So we should try to understand with the help of an example. This is the trial and error method. This is the given exact differential equation, which we hope is exact differential equation. However, the test will tell us, and when we applied the test, the value of m was this and the value of n was this. So we substituted the values after extracting them. Here you can pause the video and see this thing that we have been doing before, that how to apply this test. So the values of m and n are substituted in their respective places, but the answer is not equal on both sides, that is 2 is greater than 1. So this means that we are dealing with an inexact differential equation. So we try the trial and error method here. We are going to introduce it, and as you remember that I told you that we will experiment with different values of y and t. Primarily we start with y, and here you can see I have multiplied it on both sides, the integrating factor, assuming that it is y. So when I have multiplied it, the new form of the same equation is now this. And now to check if it is converted into exact differential equation, I can do the exactness test. Now the new value of m is this and the new value of n is this. We have noted these two values, and now we are going to substitute these values in the exactness test to see if we have achieved the exactness in the differential equation or not. So it is not equal, it is now equal, which means that now it is converted into an equation which is exact differential equation. So this is how we can convert the inexact differential equation into an exact differential equation. So this was the trial and error method. Here y worked, but if y hadn't worked, I would have tried t, and if t hadn't worked, I would have tried y square and then t square and y cube, t cube, and so on. So I can experiment with all of these values depending upon if I am unable to achieve the exactness in the differential equation. So let's talk about the other method of finding the integrating factor. It is a formula method, so it's more scientific. Let us see how we can do it. There are basically two rules to find this integrating factor by using the formula. So in this formula method, we have two rules, and in these rules, the process is that we are going to find the value of this expression, in which m will be used as well as n in 3 places, and the answer is to be found. The answer, if it is only in terms of y, that is in terms of y alone, then we will take its integral and put in the exponent, and that will be the integrating factor. Then rule 2 is there, because if this doesn't work, then we will come to rule 2. And rule 2 says that we will use this formula in which m is there in the denominator instead of n. You can compare these two formulas. They are quite a bit inverted. So by putting the values in this formula, we have to observe if the answer is in terms of t only, and if it is so, then we will take its integral with respect to t and put it in the exponent, and that will be the integrating factor. So either of these rule will hold, and that will be the integrating factor. It will be better understood if we perform a numerical example. This is the given differential equation, and we want to know if it is exact differential equation or not. So this is a small DIY. You can check it by using the exactness test, and it is expected that it will not work and it will not be an exact differential equation. These are the steps. As you can see that they are not equal to each other. So it is an inexact differential equation. So we can do it either using the formula method or the trial and error method, but here we are doing the formula method, and it has rule 1. We will experiment with rule 1 primarily, and then we will go to the rule 2 if it is needed. So this is that formula that we want to find out. We want to put the values in it, and then we have to observe the answer if it is in terms of y alone. So I substitute the value of n here, and m, and n. So after putting all of these values, I found that this is the result, which can be further written like this. So if I focus on this result, it is containing y as well as t. So this is not the desired situation. From rule 1, I expected that it will be only in terms of y. Since we have a t in this answer, so it's not in terms of y only. Therefore, rule 1 is not satisfied, and we are going to use the rule 2. In rule 2, the formula is slightly different, but the substitution is very easy. The values are substituted, the value of m and n, and the value of m. We can simplify it and we can focus on the result. It is 1 over t, which is in terms of t alone, which is something we wanted, and that is that the rule 2 is met. The integrating factor will be the integral of this answer, which will be put in the exponent. So integral of 1 over t is found here in this place, and then the exponent is taken. But we have gotten rid of the constant of integration in order to keep the thing simple, and then the answer would be in this form. After omitting the constant of integration here, we know that exponent and natural log will be cancelled out, and the answer will be equal to t. So this means that the integrating factor is t, and we can verify it by multiplying it throughout the equation, and the answer will be this. So this will become an exact differential equation. Now another thing that we should note here is that once if we find out the converted form, this will be solved as the converted form will be solved using the 4-step procedure, and 4-step procedure is something we have done before. So it is only the matter of converting the given inexact differential equation into the exact differential equation, and it is done by using the integrating factor. So this is what we have done in this video, and the remaining process can be done using the 4-step procedure that we have already learned. So this is how we fix an inexact differential equation, and we convert it into an exact differential equation by using the integrating factor. Thank you.